Hello and welcome to our weekly Fronius webinar. Today we shall be presenting the topic Feed-in Management and Data Control with Fronius Tauro. And to do this with me today is my colleague Mohammed Sidat, who is the Technical Sales Advisor for Southern Africa. He is based in Johannesburg, South Africa. And then of course myself, Cyprian Okolo, the Technical Sales Advisor for Western Africa. I'm based in Lagos, Nigeria. So let's take a look at the agenda for today. It's basically going to be split into two parts, the feed-in management part and the data communication part. So I will be taking us on the feed-in management part basically, and then Mo will now continue, we'll take over and continue with the data communication. So just going through the agenda, we'll start off with the Tauro intro, just to give you a brief info about the Tauro. And then we'll move on to concept of feed-in management. We'll now take a look at a few use cases, use case scenarios and application. And then of course, go through data communication with Mo, who will in turn give us further information afterwards. Great. So without further ado, let's now start off with a brief on the Fronius Tauro. So as most of us would know, the Fronius Tauro, actually, we have basically two variants per se. So in terms of power and specification. So we have the Fronius Tauro, which some of us will preferably call the Fronius Standard Tauro of power class with power class 50 kilowatts. The MPPT voltage range is between 400 and 930 volts. It has the three MPPT trackers, MPPTs or MPP trackers, which carries the respective current or maximum input current of 36 amps for the first two and 72 amps for the third MPPT. And then the one that installers are most used to, which is the Tauro Echo. So this comes in two power classes, that is power class 50 and 100 kilowatts respectively. So with an MPPT voltage range of 580 to 930. Of course, this has just one MPPT. And with a maximum input current of 87.5 amps for the 50 kilowatts power class, and then 175 amps for the 100 kilowatts power class. Good. Having gone through the brief of the Tauro, let's now look at the main topic for today, which is feed-in management. So, and we're going to start with a look at the concept of feed-in management. So if we now ask the question, what is feed-in management? One could basically say that it entails the regulation and control of PV systems while taking into account the feed-in limits that are usually provided from the grid operators and of course external control components, which usually in most cases are comprised of a plant controller. All these are based on predefined terms and conditions that are usually specified by the grid operator. So let's now look at feed-in management in both single and multiple Fronius Tauro inverters. So let's, of course, note here that all Fronius Tauro inverters have already integrated in them energy and feed-in management system. So this, of course, makes it possible or paves the way for an efficient system design. So power reduction is basically implemented in both software and hardware, and this provides a straightforward way of satisfying and implementing the grid operator's specifications. So let's look at conditions necessary for feed-in limitations or conditions that necessitates feed-in limitation. Let's take a scenario which entails the grid operator requesting for a feed-in limit. So this feeding limitation could, for example, be that the maximum power of feeding must not exceed a certain percentage. So for this particular example, say 70% of the total PV generator output. So in this case, appropriate output control measures must then be put in place to ensure that the corresponding parameters are adhered to at the grid feed-in point. So, depending on the type of requirement or operational condition or conditions set by the grid operator, PV systems with multiple Fronius inverters are or can be designed and controlled differently. So we shall be taking a look at these when we are handling the use case scenarios. So let's now look at the use case scenarios of feed-in limitation and the application. We're going to take it case by case. So we're going to start off with case one, which has us having a simple power reduction of an individual inverter. So that's the first scenario. So in systems containing multiple Fronius inverters, it is possible that just reducing the power of a single inverter by installing a Fronius smart meter at the grid connection point may, under some certain circumstances, meet the power limitation requirement. So the requirements will be met if and only if the formula below applies. So for this instance, if we have 3 inverters per se, and then inverter 1 can be reduced or is reduced to 0%, while inverter 2 and 3 all operate at 100%. And if all these conditions satisfies the feed-in limitation set by the grid operator, then this means that if it is possible to reach that specified feed-in limitation by reducing the power of a single inverter of the system to 0, then the above solution can be used. Great. So this junction, I would like to say for all the attendees, you can please send in your questions and we will do everything possible to answer you during the webinar or afterwards. Great. So continuing, we're going to take an example. So we have a very first example here, a system that contains 3 inverters, one of them being a Fronius Tauro 100 kilowatts, and then we now have the 2 others being 50 kilowatts Fronius Tauros. And then given that the specified feed-in limit at the transfer point must not exceed 100 kilowatts. Now, the solution to this will be basically that the output of the Fronius Tauro 100 kilowatts can be lowered to 0% to meet the feed-in requirement. So this obviously means that the power levels of the other 2 inverters, which sum up to 100 kilowatts, that is 50 plus 50, are not reduced and can continue to feed in without any restrictions. So let's move ahead to another scenario. In this case, feed-in limitation according to PV generator output. So for this scenario, it involves a PV system with 2 inverters, and the grid operator has issued strict instructions regarding the maximum permitted power that can be fed into the grid. So for this example, we have that the PV generator output is set at 200 kilowatts peak. Nominal inverter outputs are 100 kilowatts each for the 2 inverters. Of course, over dimensioning in this case has been set at 0%. And then the feed-in limit, a maximum value of 60% have been set. So the solution to this will be basically that with a maximum irradiation and at full power, only 120 kilowatts peak should be fed into the grid and not more. So in this case, we're talking about 60% of 200 kilowatts, which is of course 120 kilowatts. So this will now imply that the setting on inverter 1 would now reflect this particular percentage, and then no special settings will be made on inverter 2. So to make this clearer, we have it represented in a screenshot of settings in the Tauro setting. As you can see in this case, pardon it's actually in German, but this basically means feed-in limitation. We can see that for this instance, we have a 200 kilowatts, and then the maximum feed-in value has been set at 60%. So this is for inverter 1. So this setting, once it is done on inverter 1, you are said to have conveniently configured it to meet the feed-in limit settings or specification set by the grid operator. So once the above setting has been made, inverter 2 can feed in as much power as required, whereas inverter 1 is limited by a Fronius smart meter at the grid connecting point. And then when inverter 2 is operating at full power, it will only feed in 20 kilowatts, as you can see. So inverter 1 can continue to operate at full power, say 100 kilowatts, but then inverter 2 will only feed 20 kilowatts, making it a total of 120 kilowatts, as can be seen illustrated here. Thereby, with this control algorithm, ensuring that the grid operator's specifications have been duly satisfied. So let's look at the third scenario. In this case, feed-in limit according to nominal inverter output. So this scenario involves a PV system with 2 inverters again, and then the grid operator issues strict instructions regarding the maximum permitted power that can be fed into the grid. Now, for this example, nominal inverter output respectively are 50 and 100 kilowatts for each inverter. And then the feed-in limit has been set at a maximum of 70%. And then the solution to this would involve, similarly to case 2, that the maximum, with the maximum irradiation and at full power, only 105 kilowatts must or should be fed into the grid. So in this case, on inverter 1, the maximum feed-in setting of 105 kilowatts will be effected on inverter 1, and no special settings on inverter 2, as can also be seen in this case, reflective or similar to the previous example, or in this case, according to the nominal inverter output. So once the setting has been made, inverter 2, in as much as power, can feed in as much power as required, whereas inverter 1 limited by a Fronius smart meter at the grid connection point. And then when inverter 2 is operating at full power, it will only feed in 5 kilowatts, which would make it 105 kilowatts as required. Good. So let's now go to the fourth and final scenario, but this is actually a very peculiar one. So we're talking about integration of a plant controller. So this is applicable in situations where the grid operator demands more than just the usual power reduction. So a solution to this, in this case, specifies a set out, in this case, the solution is used if the specification set out by the grid operator cannot be met by just limiting a single inverter power. And then there is need for a permanent access for functions such as a remote shutdown or remote control. So in such instances, it is recommended that the integration of a plant controller be implemented. So we have recommendations of plant controllers, which include solar lock, meteor control, or Gartner, but this is, of course, not exclusive. This is not an exclusive recommendation per se, meaning that it is possible to use other adaptable plant controllers. So just to give us a few advantages of what is obtainable when a plant controller is implemented, it gives the ability, or presents the ability, to centrally control and monitor the commercial system. Of course, grid compliant feed-in management is made possible. Communication is also made possible with the grid operator. And then, of course, there is guaranteed safety in terms of the functions when it comes to remote control and remote shutdown. And finally, of course, but not the least, we have secure data communication to direct marketers. But in this case, we have an example of as it's done in Germany. So let's now have a schematic of what this implementation of plant controllers entails. So as you can see, we have multiple Tauro inverters with the implementation of a plant controller. And this in turn issues commands to the respective inverters on basically output function, power output functions. Of course, so there will be need for internet so as to upload data to our database and of course implement such commands. So let's have a more enhanced schematic. So this is a much more elaborate one, but this is actually to shed more light on the communication between Tauro inverters, which my colleague Mohammed Sidat will be emphasizing on later on in subsequent slides. So if you'd notice in the previous slide, there is no LAN connection. So that is why this this particular schematic was actually put in here to explain to you that it is actually necessary for inter-inverter communication. And this is made possible via LAN switch. So once you have a LAN switch, it is now possible to communicate from one inverter to or between one inverter and another. And of course, you can have your plant controller that automatically controls and issues commands via the LAN switch to the respective inverters, as can be seen. And not just that, it is also possible to have two different inverters from the same family of inverter, say a snap inverter also integrated and connected to the same common AC bus bar. So, like I said, the LAN switch in this case is what is used to implement inter-inverter communication. And this will, of course, be stressed upon or be elaborated upon by my colleague, Mohammed Sidat, who will be taking over from this point. So, Mohammed, if you are here, please, you may continue from this point as I hand over presenter rights to you.
Thank you, Stephen. Okay, moving on to the next section of today's webinar, where we will discuss the data communication of the Fronius Tauro. Starting off with the integrated communication unit. So with the Fronius Tauro, the integrated communication unit is called the pilot card. I have included an image of how the pilot card looks, but here you can see it over here. This pilot card comes standard in each and every Fronius Tauro. Basically, the pilot card will sit in the center of the Tauro inverter, and if you open up a Tauro inverter, this is where you will see the pilot card. What is the pilot card? Well, the pilot card contains your data logger, your web server, and your Wi-Fi and LAN interface all together. This will provide the basis for visualization on Fronius SolarWeb and also for visualization on the Fronius Solar.web app. With our new Fronius Tauro inverters, we no longer have a LCD display. Instead, we now have an LED status display. In terms of the open interfaces, we do have quite a few open interfaces on the pilot card. We have two Ethernet ports, okay, which can be used for Modbus TCP, Sunspec, or for Fronius Solar API JSON protocol. We also have two Modbus RTU interfaces. So if you are using an RS485 cable, that will be connected to your Modbus RTU interface. We also have a wired shutdown function on our pilot card. And we also have digital input and output ports. Why is data communication important for a PV system? Firstly, it provides a basis for complete monitoring and visualization in our online monitoring platform, which is called solar.web. It also provides a basis for potentially limiting feed-in to the grid, also for setting up zero feed-in, plant control, etc. Correctly setting up the data communication is also important for the overall monitoring of the PV system, and it also provides a basis for further settings and actions that needs to be done on the PV system, either remotely or on-site. So what are the differences to the SNAP inverter data communication? Firstly, with the Fronius Tauro, we use a purely Ethernet-based communication topology, okay? And it's strictly a star-based topology. So in this case over here, I have 4 Fronius Tauro inverters. Each Fronius Tauro inverter has a pilot card, and each one is connected with an Ethernet cable to a LAN switch, okay? So this LAN switch is connected to 4 Tauro inverters. This LAN switch will then send all the data collected from these 4 inverters to the internet router, which will then send all the data to our solar.web servers so that you can view these inverters remotely. We can also add a plant controller into the system, as my colleague Cyprian has mentioned earlier on. The point of adding a plant controller is basically to control all of these inverters. Okay, so let's say if we need to do zero feed-in, then we need to add a plant controller. If you look at the Fronius snap inverter, the communication was a bit different. With the snap inverters, we had what is called your solar.net communication ring. So here we had a in and out topology. Okay, so this is not a star topology, this is more of a in-out topology. Okay, in this particular topology, only one inverter needed a data manager. Okay, but each and every inverter needed a receiver card, which is basically the display card. So what are the main differences between the Tauro and the snap inverter when it comes to data communication? With the Tauro, all data communication is done with the pilot card. And this pilot card is equipped with 2 LAN ports, okay? And you no longer need a receiver board with the Tauro inverter. With the snap inverter, each snap inverter had to come with a receiver board. And basically the receiver board is your display board. And here we can see on the display board, you have your in and out for the solar.net. However, not each and every inverter came with a data manager. Only the master inverter needed a data manager. Okay, this is basically what the receiver board looks like. Okay, when we take it out from the inverter. So what are some further comparisons between the Tauro and the snap inverter when it comes to communication? Firstly, with the Tauro, the communication unit is integrated as standard in every device of the Gen 24 or the Tauro product series. For the snap inverter above 10 kilowatts, the communication unit is not integrated as standard. It needs to be ordered as an additional extra. For the Tauro, the initial commissioning is done by LAN or via a wireless LAN. For the Wi-Fi, for the snap inverter, device configuration possible without data manager 2. For the Tauro, every device is online because every device has a pilot card. For the snap inverter, bringing the inverter online requires a data manager. For the Tauro, data communication set up via robust and reliable Ethernet technology. And for the snap inverter, your initial commissioning is basically split into 2 parts, where you have your inverter setup, which is on a display, and your web interface, which is via LAN or wireless LAN. Also, your solar.net ring needs to be used for data communication setup. Okay, moving on to the Tauro communication examples. Okay, starting off with what is a star topology or why a star topology. Okay, so firstly, a STAR topology is easy to install. Okay, it's robust in case of failures. So for example, let's say that this first inverter, okay, the communication or the pilot card in this first inverter fails. It will not affect inverter 2 and inverter 3. Inverter 2 and inverter 3 can still send their data independently to the local router. It's also easy and fast to troubleshoot. So when it comes to troubleshooting, we basically need to disconnect one inverter from the system at a time. Okay, we don't have to disconnect more than one inverter from the system. So hence we have easy and fast troubleshooting. With the STAR Ethernet topology, we also have a maximum distance of 100 meters point to point. And this will really allow us to have good flexibility in our system design. We also have the ability to use switches to amplify signal for greater distances. So if you do exceed the 100-meter distance, you can use a switch to amplify your signal to go further than 100 meters. Okay, we're just going to have a look at a few examples with how the Tauro can communicate or can be set up for communication. The first example is that we are using the Tauro D version, which is the decentralized version, and all our inverters are in one direction. Okay. So in this case, our cable trench is in one direction, okay, and it runs directly from our communication board through to the last inverter. The distance between each inverter in this example is 20 meters. The inverter at the furthest end is 120 meters away from the router. Okay, so remember in the previous slide, I told you that we cannot exceed 100 meters point to point for Ethernet connection. So in this case, where we have 120 meters, so this inverter is 120 meters away from the router. In this example, we have to use a LAN switch in order to extend our signal. To save on cabling costs, the top 3 inverters are connected to LAN switch 2 and the bottom 3 inverters are connected to LAN switch 1. So in this case, the furthest inverter from LAN switch 2 is only 40 meters away, which is fine. And the furthest inverter from LAN switch 1 is only 60 meters away, which again is fine. Please do note that you will have to connect LAN switch 2 to LAN switch 1, okay? Then LAN switch 1 will then be connected to the internet router so that it can send all its information to SolarWeb, and it will also be connected to the plant controller so that it can be controlled by a third-party device. If you look at the second example, this is an example where we have all our inverters which are positioned irregularly. Okay, so they're not all in a straight line as I showed you in the previous image. In this case, we have 4 different trenches. So we have trench 1, trench 2, trench 3, then we have trench 4. Okay. In this particular example, I chose to go with 3 LAN switches. Okay. LAN switch 1 will be connected to all the inverters in this trench over here. Okay. So in this case, we can see that the furthest inverter from LAN switch 1 is only 70 meters, which is fine. For the second trench, the furthest inverter is only 45 meters away, which again is fine. For the next trench, again, we will use another LAN switch. The reason why we are using another LAN switch is because we don't want to exceed the distance of 100 meters. Further on, we then go ahead and use another LAN switch, which is LAN switch 3. The reason why we again use this LAN switch over here is to prevent a distance of 100 meters from an inverter to a switch to be exceeded. Please do note that you will need to connect LAN switch 2 and LAN switch 3 back to the first LAN switch 1, okay? And then this LAN switch 1 will then transfer all the data from all the switches and all the inverters to the internet router, which will then transfer the data to SolarWeb to be monitored online. The third example is when you are using a Tauro P variant. So this stands for a pre-combined Tauro. Remember, when you are using a pre-combined Tauro, you will need to use DC combiner boxes. Okay. In this case, the inverters are arranged centrally next to the transformer. The strings are collected with DC combiner boxes and then connected to the inverters. The LAN cabling is also installed in a STAR network. So in this case, you can see that we are using DC combiner boxes. Okay. So your panels are connected to your DC combiner boxes, and your DC combiner boxes then collect the DC from your panels and then send it directly to your Tauro inverters. So in this case, we have 6 Tauro inverters, okay, which are all P versions. And we have chosen to install all these inverters directly next to each other, okay, which might be in some central location, which is usually very close to your local transformer. In this particular example, I can choose to use one LAN switch and connect all my Tauro inverters to the single LAN switch. The reason for this is because my LAN switch would be as close as possible to these inverters, because all these inverters will be in the same room or on the same wall. Moving on to the next section, where we will discuss your different LAN switch types. We will start off with the first one, which is your standard Ethernet switch. What is required to implement a standard Ethernet switch? Well, firstly, we need a box with IP protection and a power supply. And we need a standard Ethernet switch. Okay, so in this case here, we've got our standard Ethernet switch, which is placed into a box with IP protection. And this box basically has an integrated fuse and an integrated AC to DC converter. Okay, remember, it needs to take the 230 volt AC that it receives from the grid, and it needs to convert it to either 12 or 24 volt DC for the switch. The second type of switch is your power over Ethernet switch. What is required to implement a power over Ethernet switch? Firstly, we need a box with IP protection. Okay. Secondly, we need a standard PoE, which stands for power over Ethernet switch. If you have more than one PoE switch required, then the main switch, which is the very first in the chain, needs to have a PoE out port. Okay, so we're talking about the switch over here. The first PoE switch in the system can forward the PoE signal to other switches and is therefore the middle part of the chain. Only a limited number of PoE switches can be daisy chained due to the limited power transmission capacity over Ethernet. So if you are going to use a switch, please do take note of these 3 points. Okay, so here we can see we have 2 Tauro inverters, okay, and each of them are connected to 2 separate PoE switches. Moving on to the next switch, which is basically termed your outdoor standard Ethernet switch. What is required to implement an outdoor standard Ethernet switch? Well, firstly, you need the outdoor switch itself. It is usually a 12 or 24 volt switch, but I would suggest that you do get a 12 volt switch. The reason for this is that you can connect or power up this 12 volt switch directly from the pilot card itself. Okay. The reason for this is that our pilot card has a 12 volt power output. And in this case, you will not need to use any adapter. The switch can also be connected to the AC area of the inverter. And if you are going to connect it to the AC area of the inverter for the power supply, please make sure that you do provide the switch with its own power adapter. It's usually an AC to 12 volt DC power supply. Okay, so in this case, I'm powering the switch with a 12 volt DC signal directly from the pilot card. And in this case, I'm powering the switch from the AC, which is coming from my inverter. Okay, the next example is an outdoor power over Ethernet switch. So what is required to implement an outdoor power over Ethernet switch? The switch is supplied by power over your Ethernet cable. So in this case, we don't need to supply any power from the inverter itself. The power that the switch gets is from the Ethernet cable. Okay, so there's no direct power cable. Power comes from your Ethernet cable itself. The next example is your built-in switch in the Tauro. So if you want to, you can install a switch inside the Tauro itself. The reason you can do this is that we do have a generous amount of space in the Tauro, and this allows you to place the switch inside the Tauro itself. Okay. Remember, if you place the switch inside the Tauro, the switch will take on the IP rating of the Tauro, okay, which is your IP65 rating. And this will basically lead to cost saving and installation effort saving as well. Okay, remember, you can power up the switch from the 12-volt power supply on the pilot card. Okay, so again, it makes it very easy and straightforward if you are going to use this method over here. Okay, for further information, you're more than welcome to go to our Fronius website where you can download all our catalogs, etc. You can also have a look at our YouTube where we have all our webinars that we have hosted for the Sub-Saharan Africa region. You're also more than welcome to contact one of your technical sales advisors, or alternatively, you can also contact one of the particular Fronius departments. From my side, I'd like to thank you for joining today's webinar. We will be keeping the Q&A session open for the next 5 minutes. So if you do have any questions, please do post them. Thank you very much for attending today's webinar, and goodbye until next time.